Welcome to day 2 of This is AI. Again, thanks for everybody who joined us yesterday and are rejoining us today. Appreciate your enthusiasm to and encourage you to continue on your learning journey. We have a great session planned today, but before we get into the session, just some housekeeping. For those who want to ask questions, there's a side panel where you can ask the questions to the panelists, and we will be having a panel Q&A towards the end of the session, where we will cover some of the questions that we have prepared and also some of the questions that you may have. For the agenda today, so yesterday, for those who attended yesterday, just to kind of, so before we go there, some other housekeeping announcements on what is currently planned by the EPRI, around AI. We have a reverse pitch coming up and also an electric power summit around AI. So please go to the website and please do sign up because there's a lot of work that's currently going on in this space. And this is something that all utilities are interested in looking at, and there are significant advances that are being made in this space. So those who joined us yesterday, I'll kind of briefly recap a little bit about what we discussed yesterday. We discussed what is AI. Yesterday, we talked a little bit about the technology and some of the AI techniques that are being used in the industry. We talked about the importance of data in AI, as well as some of the how do you explain AI? That's a very huge topic within the industry that we discussed yesterday. And we did see some examples in the power and electric industry use cases yesterday. So today, what we're going to cover is a little bit more advanced, a little bit more cutting edge. We're going to talk about some of the upcoming R&D that's happening in AI, and we have a number of distinguished speakers that will be talking to us about it. And then we will close it out by me moderating a panel with all the different speakers that presented today. So with that, let me introduce the first speaker, Ramanathan Guha from Google. Will talk to us about the first topic.
Hi, should I start?
Yes, go ahead.
Okay, great, thank you. I'm going to talk to you about this project that we've been building at Google for the last 3 years called Data Commons. But before we jump into the project itself, I want to take a step back and try and place all this interest and excitement around data science and machine learning in the context of hardcore engineering. It's my position that it all has to do with the evolution of what we consider models. Much of the advance in the last 300 years in engineering has come from building explicit models. Sure, there was engineering before models. There was no explicit model of St. Peter's Cathedral, but when you wanted to go from St. Peter's Cathedral to Burj Khalifa, we needed explicit models. I'm fairly sure the Wright brothers didn't have models of airflow when they built a Kitty Hawk plane, but when you need to do the Airbus, you do need models. At the end of the day, what is a model? Most of the kind of models that we use in engineering today to build these kinds of structures are what I call analytic models. The basic equations of continuum mechanics, materials, heat transfer, the Kirchhoff's laws, and so on and so forth, that capture core causal phenomenon in equations. In fact, if you look at a standard engineering, undergraduate engineering curriculum, you have a course or a sequence of course devoted to each family of these equations. And this is our notion of a model. And this modeling enterprise has been incredibly successful over the last couple of centuries. Yes, and computers came in, and when we started building far more complicated artifacts, we needed to introduce finite element methods for more complicated cases. So if I'm not mistaken, the slide rule was invented around the time that the Golden Gate Bridge was built because the calculations were getting too tedious. And when you needed to go and figure out that the 787's wingspan, the wings can flap up to a maximum of 26 feet. And remember that the next time you're on a 787, we needed far more complicated calculations, but still these were manually built models using a small number of different types of equations, capturing the underlying phenomena. The problem with this approach of analytic models is that we don't have basic or causal equations for social, medical, behavior phenomenon. And more we are being called upon, especially in times like trying to predict. It would have been great if we could have predicted that certain behavioral patterns would lead to waves of pandemic or having so many things having to do with the climate, having the interaction between economics and poverty and climate and people moving around and so on and so forth. Essentially, classical engineering has proved not that useful. Over the last 15, 20 years, there's been a new kind of modeling, for want of a better word, which is what I call empirical modeling. It's take lots of data and fit the curve. That is machine learning. There's no causal equations required. In the early days, they were fairly simple forms of equations, and now you have incredibly complicated systems with tens of millions of parameters. You need really basically just two things, which is lots of data and lots of compute power. And these things have been massively successful in the last, actually more than 10, 15, 20 years. The first example actually, where people went like, wow, you can do that, was Google spell correction. Google tried to use a standard dictionary-based spell correction mechanism for a number of years, but it didn't really work that well. Not number of years, number of quarters. It didn't really work that well. There were too many terms in the, Britney Spears doesn't show up in the dictionary, at least not at that point in time. They looked at, they used the entire web as a corpus and a few models of how people could misspell things and created their spelling correction. This was followed by its use in advertisement, in news feeds, and more recently you have vision and speech and so on. But the interesting thing is that these are mostly web ecosystem products. But so much more can be done than just these kinds of web optimizations, which are, even speaking as a web person, I can say this, they're not as real and hard and pressing as the kinds of problems that are pictured on the left side of the screen, the climate problems and health problems and so on and so forth. Yes, it's great that we can figure out that if you say, chips in Silicon Valley, you're more likely to refer to kale chips than some other kind of chips and so on and so forth. But really, we could do more with this technology than just that. So what is holding us back from applying data science, machine learning, AI, whatever you want to call it, to 10x more problems? There's three pillars to machine learning. One is the algorithms, all kinds of regression, support vector machines, deep neural networks, LSTMs, GANs, attention mechanisms, transformers, whatever. The interesting thing is that most of these algorithms are now open source. Gone are the days when Oracle's core algorithms would be kept locked away, and it's not like those days. Everything that is interesting is now available on GitHub. The second pillar is compute. Well, even that, thanks to the advent of cloud, is kind of being democratized. You want to get your hands on, 1,000 GPUs or TPUs, you can do it. And you don't need to lay out as a huge capital infrastructure. You can pay as you go, and this is really of course you have to pay, but this is really so much data, and that's the big frontier that I'd like to talk to over here. And the reason why all of these advances that we've come from web companies is because these companies, right from day one, were focused on data, because that's what they are. They're basically data intermediaries, so they understood the value of data, and they kept making sure that the data was curated and kept in a fashion where, as the algorithms developed, newer and newer models could be learned based on these things. Data is the AI enabler. Easily usable data set research direction. My favorite example of this is Jim Gray's Sloan Digital Sky survey, where in the late 90s, he realized that there were only some number of data sources for astronomy information. It's a fairly limited number. It could be counted in your fingers. He managed to, using help from the Sloan Foundation, get access to all that data. And he pulled it together in a set of databases and SQL Server databases and provided access. He aggregated the whole thing and provided access to basically every astronomy researcher on the planet. It utterly, completely changed the nature of astronomy research. More recently, we've seen ImageNet, and ImageNet has been a crucial part of making progress in vision research. And it's not just here, it's in Raj Chetty at Harvard's incredible data collection around opportunity insights is setting new kinds of ways of looking at how the different factors that contribute to economic progress. So the question is, how do we enable this for every science, for every social sciences and biological sciences and climate sciences and so on a very large scale? The problem is not a lack of data. Now, we all agree that data powers everything, journalism, policy, machine learning. The problem is not a lack of data. If you look at societal information, you have Census and FBI and BLS and BEA and EIA, and there's 16 federal organizations that collect data. The situation in biomedicine is even more dire, where you have, the Campbell databases about different molecules. You have ENCODE, you have DBSNP, you have protein databases, and researchers spend a lifetime in one cluster of these databases. And these databases are huge. The people are typically not computer scientists, and the infrastructure is really big. And we all know, like in climate, you have similar NOAA, EPA, EIA, and so on and so forth. The problem is using this data. You have to forage for the data sets, track down the assumptions, clean, normalize, join. It's really high upfront costs. We take our inspiration from satellite. In 2002, 2003, NASA had most of its Landsat images up on its website. In theory, if you wanted to figure out what your house looked like from the sky, you could go figure out the right tiles that you have to download, get the right Java applet in order to stitch these tiles together, get, I think, the same or different Java applet to view these tiles. And the reality is that nobody did it because it was so complicated. In 2004, Google Maps launched and utterly changed people's view of satellite imagery and the importance of satellite imagery in their life. You could look at anything that you wanted. We have a similar situation today with data. We talk about things like the correlation between COVID and race, or COVID and poverty, or this or that. You could, in theory, answer these questions by looking at data that is available publicly. In practice, it is so hard. Nobody does it except for a few places at the New York Times or some other places which have, it's where it's part of their job. Imagine instead if you could just turn around and ask Google or Alexa or your other favorite search engine, how much that would change things. And not just that, every data analysis platform, Scikit, TensorFlow, Python notebooks just came with this data. That's the goal that we're aiming at. So what we've been doing over the last 3 years is we've taken a fairly large number of these different databases, cleaned up the data, done all this data wrangling just once, don't have to do it again and again and again, aligned the schemas, built new schemas on top of schema.org, and built this giant knowledge graph, which has all this data. The issue is that this knowledge graph is way too big for most people to download. So instead, what we do is we provide cloud APIs so that applications can be built by, for and by journalists, students, search, news, researchers, and so on and so forth. To distinguish between this knowledge base, this knowledge graph, and collections of data sets. There's several collections of data sets over there, like Harvard's Dataverse, data.gov, and even now search engines over things like these data sets, like Google Dataset Search, that try to solve the problem of finding the data sets remain. You have to clean the data, you have to download the data, clean the data, etc., etc., etc. Data Commons, in contrast, is a single knowledge graph built by cleaning, normalizing, and joining all these data sets so that it's much easier to use. What we've built is an open source infrastructure for creating, storing, and serving these knowledge graphs. It's right now running on Google Cloud. In theory, you should be able to run it in other clouds. We can have multiple instances of this. We've also built two large, actually very large knowledge graphs based on this infrastructure. One is what we call the societal KG, which is demographics, education, crime, and so on and so forth. And the second one is a biomedical knowledge graph. And we're just starting work on a climate and energy data commons. The societal KG has data from census, health, economics, labor, crime. It has even elections, education institutions. Most of the data is about the US at the level of every state, counties, census tract, city. But we do have data at admin level 2 level across the world. And the data is kept updated all the time. It's approximately 1.2 billion time series, and it's expanding very fast right now. The applications of these things are interesting. One is a big application in Google search. There's data exploration tools and data science students. Everything that I'm going to show you now is available on either on google.com or datacommons.org. So let me just walk you through a few examples of the stuff to give you an idea of the kinds of things that we can do with this. So you could go type in, a number of poor Hispanics in San Jose. The range of these kinds of queries that you can ask is incredibly large. And it'll give you the answer, and you don't have to go hunting in different places. And then you can go do explore more, the little explore more button over there, and get an enormous amount of breakdown of data about whatever place you're looking at. It could be a city, a zip code, whatever state, whatever. There's data about health and equity and crime and education and demographics. There's also other tools over there to show you things. The second category of views is doing analysis. This is actually a Python.
Gua, your audio is going out pretty bad. Your audio is cutting in and out. Can you hear us okay?
I can hear you okay. I'm going to continue because I mean, other than stopping, I don't know what to do.
Okay, that's fine.
I can try different. Is this better? Hello?
Yeah, that sounds pretty good.
Oh, my mic, okay. So this is a Python notebook that is in use by one of the upper division data science courses in one of the top universities, where the goal is for students to build a model of obesity as a function of blood pressure, unemployment, and poverty line. This tutorial is available on the Data Commons website. The interesting point is that if you were to do this from scratch, it would take on the order of many days or weeks to get all the data together. But if the data is available as part of the platform, and this is the whole point. Today, we look at different libraries as part of the platform, and we expect to be able to use sklearn or various other libraries from anywhere. Imagine if you could do the same thing for data. That would be awesome. And you can go in to see what are all the interesting results that the students derive and things like that. There's a bunch of other tools over there that I won't go into in the interest of time. So the kinds of questions like, what is the correlation between COVID and gender, or COVID and race, COVID and this, etc. These answers can be derived in a matter of literally 10, 15, 20 seconds, as opposed to having to go make it a multi-week exercise. The other exercise that we're doing is, together with Stanford, we're building Stanford and ISB Science in Seattle, we are building a biomedical data commons, which has all of these data sources, again, built as a single big graph. We just had the first PhD thesis defense based substantially on this work last summer at Stanford, and the person who built this data commons, Samantha Picos, is the one who did that defense, and she's continuing work on that. So going forward, our goal is sort of many data commons from many providers, energy, climate, biodiversity, and so many more. But the idea should be it's one API, one schema, so that you can go from one kind of, you have a uniform way of talking about a place, about people, about measurements, about and so on and so forth. We expect that some of them will be public and some of them will be private. Some of them will be semi-public, meaning that you have to sign some kind of a thing in order to get access. Some of them will be free, like the global one. Some of them will be paid. They'll have, depending on the kind of thing you're in. And of course, the big thing in all this is the role of the Data Commons project had the same role as the Mosaic project played for the World Wide Web, which is we built a first version, made it providing all our code as a reference implementation and all of the data that is in the current Data Commons available to everybody to jumpstart the process. And we're looking for collaborators. So with that, I will hand it over to the next speaker.
Thanks, Ramanathan. Before I turn it over to Dave, there's a question in the audience about Wolfram Alpha and where that fits in with ML and AI. Do you have any comments on that, Ramanathan?
Yeah, there's a lot of similarity. The Wolfram Alpha, Wolfram did, took a bunch of data sets, aggregated them, and provided a natural language interface to them. I think it's a fantastic exercise. I think it's one-off. To my knowledge, you can't go take that entire system and expand it. You can't go use that infrastructure to build a climate knowledge graph or anything like that. So I think it's a fantastic exercise. But what we're trying to do is to take it from an instance. And Wolfram Alpha's thing was in the spirit of many earlier AI projects like Psych and so on. And what we're trying to do here is sort of build a platform and make it an open thing.
Thank you. Thank you. Over to you, David. You're on mute.
I'm calling in on the phone and my phone is unmuted. Can you hear me?
Yes, you're good to go.
Okay, thank you. Great, well, thank you so much for having me. My name is Dave Biagioni. I'm in the NREL Computational Science Center, and really appreciate hearing the thoughts of Ramanathan in the previous talk, and I'll try to tie together some of the concepts and perspectives that I talk about here to things that he said. To give you a little bit of perspective, I'm a researcher, I'm a mathematician, and so my perspective is going to be coming from a very different place. I'm also going to be a little bit more focused on power systems, AI as applied to power systems in this presentation. It's something that I've worked on a fair bit. So kind of where I'm coming from, I have an applied math PhD. I've worked in the industry. I was a data scientist and engineering manager for IBM Watson Discovery, which started off as a Denver startup, AI as a service startup. So I have experience there building software, thinking about and use cases for customers and things like that. I'm currently a senior scientist in the Computational Science Center. I'm a PI for 2 internally funded R&D projects focused on AI and ML. I organize and host a weekly scientific ML AI seminar series, and so I kind of have a good perspective on what people at NREL are doing and applying these techniques to different problems. I'm contributing to a bunch of projects that are pretty much all using AI or ML in some sense, and the domains range from transportation and power systems, buildings, to chemistry and materials. And so my perspective is one of collaboration primarily. I'm an applied math person by training, and so I spend a lot of time collaborating with domain experts to find challenging problems where we can bring applied math, AI, ML, advanced computing, and simulation as a general sum, and maybe this is a little bit of a twist on how speakers will present, the notion of using AI in this context. But we'd like to try simple things first. Don't shy away from pushback, especially from domain experts who know the subject matter really well, and be skeptical about it. It's not that the hype isn't warranted in many cases when it comes to AI, but it's also good to just understand what you're really trying to do and how applicable a given method is, and not necessarily jump at it just because it has the word deep learning in it somewhere. And so I have a fairly high level, pretty good view, I think, at NREL of how people are applying AI to power systems in particular. And so I reached out very informally to a number of groups, group managers and researchers who I know work at the intersection of AI and power systems, just to kind of get a feel of what they consider to be the topic areas. They didn't necessarily present them in this way, but I kind of categorized their responses into a number of topic areas where the researcher believes they're applying AI to power systems from some angle. And so, roughly speaking, it seems like the application areas break down into databases and benchmarks, forecasting, state estimation, simulation, or really guiding simulations, and then decision making and optimization. And I would kind of argue, my perspective, having been at this for a while now, is that many of these tasks really are more statistical models. We can call it AI if we want to, but oftentimes if you're trying to predict, a value in a time series, people have been doing that for a really long time. And way before deep neural nets were a big thing, and people were throwing around the words AI or ML. And so I think a lot of these things really we would call statistical modeling, one shape or another, that are these days using things we associate with AI like deep neural networks. I would say the one exception to that, from my perspective, and the area that I kind of work on most closely myself, is in the decision making. The notion of kind of having an agent that can decide what to do, how to control, or how to design or optimize a system based on experience interacting with that system. In my mind, this is maybe the most closely aligned sort of topic area with what I think of as AI, and it's the area that I work in most closely myself. So I'll talk about that a little bit here. Again, that mostly as it applies to power systems specifically. So I want to draw a little bit of a contrast to the previous speaker. I think that he made a lot of good points about how analytic models have driven a lot of technological advances in the last 300 years, and I think we would all agree with that. But one of these sort of angles I bring to perspectives I think I bring to the table here based on research at NREL is that case, especially in power systems, that you want to consider a spectrum of decision-making modalities, ranging from approaches that are purely model-based, using analytical models, using the physics that we know of, and spanning on the other end of the spectrum, model-free. And I think the tension right now in power systems and AI is that there's a draw in both directions. The push for using model-free methods that sort of don't require any kind of analytical model of the physics. There is a lot of kind of hype and excitement around that right now, and there are some advantages to using model-free methods. However, it's also the case that in many problems related to power systems, I'm showing here some equations. I'm not going to go into any detail with the math, but for DC-OPF, you have a convex optimization problem, you have a model, you can solve it using off-the-shelf solvers with very good, very efficiently and with guarantees about uniqueness. It's my point of view that this spectrum is a very important one, and thinking about where models play a role, if models play a role, what the pros and cons are of using a model or not using a model in an approach, is just some things to think about when you're approaching a new problem. So this little table here is more of a straw man than anything else. Kind of highlighting, model-based methods using analytical model lets you enforce physical or safety-oriented constraints. Potentially, if you convexify your problem, you can find a unique solution. Which, when you're doing unit commitment with one-day look ahead, for example, at a utility company, you'd like to have some guarantees about your solution potentially. And model-free methods, on the other hand, learn directly from data. So if you have a simulator, you can run that simulator a bunch of times and learn some kind of control policy based on that interaction. You can also generate decisions very quickly with model-free methods, especially if you're using neural networks, because effectively a decision is equivalent to making a forward pass on the neural network. And so I thought what might be interesting to think about here is just I was going to provide two examples of projects I worked on personally, so I'm not trying to necessarily pitch them as being anything more special than anything else happening at NREL. I just happen to be familiar with what the details are. I thought I'd provide two examples of how we kind of can think about this spectrum and sort of how the different parts of the spectrum might interact to kind of get a better end product that uses AI, but maybe not exclusively. And so in the first example, we had a paper last year that was basically combining machine learning with the traditional method. So we said, hey, if we have a good optimization-based model, we know it has the sort of physical constraints implemented, we know we can solve it with some guarantees about the solution, but it can be kind of slow to converge, and we're just throwing away all the information. Every time we run this algorithm, we throw away all the sort of past history. Couldn't we find a hybrid method that accelerates the traditional algorithm, which is called ADMM, by injecting machine learning? And so the idea was to try to speed this traditional method up. It's a distributed control problem, distributed DCOPF. Couldn't we speed this traditional algorithm up by kind of using ML to guide the iteration, but do it in a way that's stable, meaning that machine learning, any errors in the predictions won't sort of throw the entire thing off the rails. And so I'll point you to this citation here if you're interested in the details, but the high level result was that the hybrid method outperforms either individual approach and is robust to prediction error. So even if our machine learning model has prediction error, which it inevitably will, the algorithm is still convergent and sort of has all the properties we want from a model-based method. So the takeaway for this, for me, was that hybrid methods can combine safety-centric characteristics of the analytical model with learning and data. And so this is a really promising way, in my opinion, promising direction for applying AI to power systems. The second example I wanted to talk about is slightly different in the sense that we wrote a paper and it's focused on smart water heaters. So it's really more of a device on a power system than the power system or the grid itself. I'm not going to get into the details of that other than to say, we spent some time actually comparing. We said, hey, let's look at a model-based approach to solving a control problem versus a model-free method. And so we said, all right, let's start our benchmark be a model predicted controller. So NPC model. We write down all the physics of this water heater and the way the temperature evolves and all that. We give it perfect information about the physical model, so there's no error in the model the way that we simulated the system. The NPC model perfectly matches the simulator physics, and we give it perfect forecasting. So it knows exactly how much demand there will be in the household when this water heater needs to take that into account. Shouldn't this be about as good as you can do? An NPC controller with perfect physics, perfect forecasting, shouldn't that be about as good of a controller as you're going to find? And well, it turns out there are challenges even with this sort of perfect setup. Again, it's sort of a benchmark with perfect information. It turns out limited look ahead for NPC models in the absence of a good cost to go or value function. Actually, the NPC models will struggle with this because they don't have a good model of the future beyond their look ahead horizon. When you add stochasticity, which you have to do because these systems are all stochastic, there are all kinds of exogenous disturbances. For example, how much demand there will be on the water heater at a given day. How does NPC handle that? It's not totally obvious how you do it. We investigated a number of different methods of sort of forecasting under uncertainty into the NPC model. Also, it can be really expensive. It turns out even for the simple water heater model, with a far enough look ahead with enough stochastic scenarios, if you're doing stochastic programming, for example, you have binary variable constraints because of the on-off control. It turns out you can make a pretty intractable computational problem trying to solve NPC at every control step. And so we thought this was a great benchmark because it kind of thinking on some level you can't do much better than this. But what happens when we throw a model-free method of this using only a simulator of the physics? And so the result was that model-free methods actually, on average, had better control performance on held out evaluation days, and they're orders of magnitude faster to use online. That's a huge plus to using these model-free methods. We actually investigated scaling a little bit for this study, and we used the HPC system at NREL. And it turns out we were able, once we scaled the problem up, up enough, we could train the entire policy in less time than it took to run a single control step with NPC. And once you train the policy, it's the policy. You can just run it online. Again, forward passes through neural network. It's very fast. And there's no additional training is needed unless, it might be in some cases, but for purposes of this study, we trained it in 90 seconds. We used 1,100 cores, CPU cores on Eagle, and we were done. I mean, you could basically run the policy against all the evaluation days you wanted, and it was doing just as well, if not slightly better, than the NPC model with perfect information. So the takeaway here for me was that, when possible, model-based methods can provide good benchmarks, and they can build confidence in your AI solution. On the other hand, hardware acceleration and distributed computing, they're much easier to leverage than off-the-shelf solvers. So Gurobi, which is what we used for the model-based approach here, is a very good commercial software solver for convex optimization and non-convex problems as well. However, it's solving a very difficult problem. If you think about NPC with a long look ahead with a binary control, you're effectively looking at a combinatorial search problem. And as good as Gurobi is as a general purpose solver, it was easy to scale the problem up to where they really couldn't solve the problem in a tractable way. And in contrast, again, because we can scale up in an embarrassing way some of these model-free methods, and they ultimately learn a neural network where you're just doing a forward pass to get the control sequence for a given state. It was just orders of magnitude faster to use the model-free method in this context. But we were able to build confidence in the solution because we could compare it and benchmark it against this model-based method. And so, yeah, concluding remarks and just sort of ruminations about this, combining traditional methods with AI is a promising approach, especially for power systems, control, planning, and optimization. Traditional methods play an important role in benchmarking and encoding domain knowledge and safety critical constraints. That's one thing where kind of in contrast maybe to the previous presentation, I think this is a really interesting and ongoing research direction for AI, is how do we take, and not have to learn everything from scratch, but if we have domain knowledge and based on experience and based on sort of many centuries, for example, of developing a field, how do we condition our learning on that knowledge? AI-based methods, in contrast, can learn directly from data and often more scalable. And this is a really exciting and burgeoning area of research and worthy of further investment, in my opinion. So with that, I know I'm kind of went a little bit long there. Thanks for your patience. Thanks for your time.
Hey, David, thanks a lot for the presentation. Just a question before you go from Tamer Ibrahim about training the model will take a lot of time, and if we add new lines and generators, etc., do you think that what's your opinion on updating the model? Like, does it take a lot of time? How much time does it take?
All right, for which model?
So there's the question on the chat is that when you're building models, you're building models with existing data, and if you add new lines and new transformers and new equipment onto the line, do you have to go and update the model, or the model will be updated automatically?
I'm having a little trouble hearing you. Are you talking about the first example? I'm looking in the chat here.
It's the reinforcement model.
The reinforcement learning model, yeah. So we do, in that case, the downside, the challenge, and where there's almost a need to have a scalable solution is that these model-free methods, one of the main challenges of using them is that they're sample complex. And that means that if your simulator is slow and takes a long time to sort of run a single episode, for example, to give the agent data to learn from, that's the main challenge for the model-free methods. They need to see oftentimes lots and lots of simulations before they can learn a good policy. This is yet another area, though. We're talking about reinforcement learning in particular, that model-free approach, where model-based methods, in fact, Google DeepMind is at the leading edge of this in some respects. There are newer methods now that are incorporating models into the reinforcement learning to address the sample complexity. So if you have a little bit of additional information you can put into your learning, you can reduce the sample complexity because you can think of it as kind of conditioning the learning on knowledge of some kind that you have ahead of time, or a prior, if you want to think of it that way.
Okay, thank you. The next speaker that we have is Yashwant from EPRI. Yashwant, all right, take it away.
Thank you, Mukund. Thank you for the awesome presentations, Guha and Dave. So I'll be here on day 2 for This is AI. If you've been a part of day 1, welcome back. If you're interested in NLP, this is something next 10 minutes are gonna be a blast. So here, I'm gonna be walking away from the spectrum of these presenters today, and I'll be talking about a really high overview about a really cool NLP architecture. I'm not going to go into the deep details of it. I'm going to talk about its challenges, its applications, and what's coming up in the future. And we're going to talk about transformers. So transformers has a really funny history, at least for me. When I was in school, it was all about Autobots, fighting Decepticons. It was Bumblebee, it was Optimus Prime. But when I moved to college, I come from an electrical background, so Transformers was all about generating electricity. But still, that was pretty cool enough. But now here I am working as a data scientist, and Transformers actually got even more cooler, even though they don't really look cool on paper. As you can see, the figure on the extreme right is a really simple architecture of a transformer model. So transformers basically are natural language processing model architectures that are capable of really good language predictions. That's basically the overview. And so OpenAI, which was initially founded by Elon Musk, it's a startup, and they're doing extremely remarkable research in AI. And one of their brainchilds was a transformer model called GPT-3. So GPT-3 is obviously a successor of GPT-2, which is a successor of GPT-1. But we're going to talk about GPT-3 a little bit in detail because it's the more recent advancement, and it's super cool with the things that you can do with GPT-3. And the best part about it is it's open source. You don't need any sort of a license to use it. The GitHub repo is open for all. You can just go in, grab the code, clone it, and start using it right away. So GPT-3 is a model with 175 billion parameters. So a parameter, let's say, is a moving part of a model. A really small models have a few hundred parameters. Moderate-sized model have a few 1,000 parameters. Really big models have a few 100,000 parameters. So we rarely hit a million mark, but GPT-3 has billions of parameters, over 175 billion parameters. So it's a really, really, really complex model. So it probably might have learned a lot about the English language, right? So it just takes 300 gigs of RAM to just load in the weights of the model. So to put it in memory, to make predictions, you need to have 300 gigs of physical RAM or virtual RAM if you're even trying to make predictions on your local machine. One of the really interesting points about GPT-3 is it doesn't need any sort of tuning. So one of the things that's really common with machine learning models is you need to tune them before you get really good results. But GPT-3 gives state-of-the-art results without any tuning. So you take it straight off of the oven and you start munching at it, and it's going to taste really good without any seasoning on top. And the performance of models usually plateaus after a stage. For example, if you're training a really deep neural network, the performance kind of starts plateauing after it hits the 90-95 percentile because it just can't learn any more of the lower level implementations of the data anymore. But GPT-3 kind of keeps going. It just keeps getting better. Even at 98 percentile, it keeps going to 99 and keeps pushing the limit. So there's the scary thing about GPT-3 is it has no upper bound. It can keep learning and it can just go beyond our own understanding of the English language. I'm taking English as an example, but GPT-3 can be trained on a lot of other languages as well. All right, so the performance, as I've talked about before, it has billions of parameters, but let's talk about tokens. So token is a word or an entity in the English language. Like the word model is a token, the word the is a token, numbers, symbols, Roman numericals, everything's a token. So GPT-3 has 500 billion tokens. Think of it as a dictionary with 500 billion words in it. And it has learned the definition, the relationship, the sort of a intrinsic value of each and every word, which is a token. So so if you had to put that dictionary in memory, it would take 700 gigs of storage, and that's massive. So one of the things which I've spoken about before is GPT-3 keeps improving. It needs to know hyperparameter tuning. And it does really well with just a little bit of data or a little bit of training to be exact. So it's a great step towards generalization. And so GPT-3 is kind of like an open black box. Like you can put your hand in it, but you don't know where your hand's actually going. So it's kind of like a blind search, but there's a lot of things you can hit in the way while going through that black box. So we're in a spot where training models used to take months or years in the past, let's say 20, 25 years ago, but now you can just train it in a few hours. So we're at a point where processing is, model training in terms of CPU performance is not the upper limit. We're at a stage where we can train a 175 billion parameter model over the course of a few months, and that would technically have been impossible if we were talking about this 20 years ago. So as Peter Parker says, with great powers comes great responsibility, right? So GPT-3, because it has tremendous power of predictions of the understanding of the English language, it can be used to make really authentic sounding articles. So if you had to take a look at two different news articles, and you put them side by side, you wouldn't be able to tell which one's written by a human and which one's written by GPT-3. In fact, it's not even going to be a 50-50 split. You're going to lean more towards the GPT-3 model because it has all of those small niches of a human written article. At the same time, even though that's a really good thing, writing really authentic news articles kind of saves a lot of downtime on generating new content. But at the same time, it can be used for misinformation as well. We spoke about deepfakes yesterday for day one. That's one of the areas where you can just take a really learned model that knows how to emulate human emotion and human language and use that for a really bad purpose. So that's one of the areas where it's ethically concerning, and it requires us to put an ethical boundary saying that, okay, GPT-3, you've learned way too much. Here are your hard-coded bounds. So that's something really important. And a key factor, which I probably have not mentioned on any of the slides, is even though the GPT-3's billion parameter model, it's not open to the public. A small version of it, a small curated ethical version of it is only out because something that knows the entire Wikipedia is really bad in the wrong hands. So we have a curated model, and that works extremely well. Just imagine what the full model is capable of. All right, now let's talk about some really cool use cases. I've seen over 300 use cases of the GPT-3 model. The three of them that I've presented here in this slide is playing Dungeons and Dragons with a transformer model. So imagine your dungeon master is actually an AI bot, which is generating new storylines as the game progresses. And it knows, it probably has seen, like, I don't know, a few million Dungeons and Dragons games, so it knows how the flow goes. When it gets too boring, it puts in a surprise element and all of that. It's learning over time, and it keeps getting better. The other use case is a blog idea generator on the right here. Basically, you want to write about something, but you just don't know how to start or how to end an article, right? You type in the topic you want to write about, and it's going to generate content out of nothing. This is not a classification model where it picks a random article from the internet and says, hey, this is similar to the blog that you're trying to write. No, this writes everything from scratch. Like this, the article that it writes is probably, it's something that it has never seen in its training, and it's something that no human probably has ever read or written. And the last but not least example of a use case is generated voice and styles. So you can make, I don't know, Taylor Swift sing a death metal song with her voice. The lyrics are going to be from a death metal genre, but you can make Taylor Swift sing it. Similarly, you can make Eminem sing, I don't know, a really slow song, a Taylor Swift song, or even uh, any song of your choice. You can make him sing in an Indian language as well with his style, with his rap. So the possibilities are endless, right? Again, comes back to great power comes with great responsibilities. We're going to talk about something that OpenAI did with all of these different possibilities. So OpenAI, the startup that has built up with GPT-3, went back to the board and said that, okay, let's build a really cool use case that mixes natural language processing with vision. So deep learning is kind of like a Lego box, right? You take in different parts, you kind of build a structure, and you're like, hey, this is cool, but I can make it look better. So you swap out a bunch of parts and you put in new parts and you have an upgraded model. Deep learning kind of works in the same way. And an example of one of the extremely amazing use cases of GPT-3 built by OpenAI itself was released earlier this year, I guess late January. It's called DAL-E, which is a play of words using Pixar's Wall-E and the artist Salvador Dali. So Dali is extremely good at creating images from text. We've seen image captioning, which is taking a picture and describing what's in the picture, and that works pretty well. But what about the other way around, taking text and generating an image, which probably doesn't even exist on the entire internet or in the entire history of human beings? So you can see a lot of really cool examples on the right. Um, an armchair in the shape of an avocado. Probably nobody's really thought of it. Like that didn't even struck in any artist's mind. But DALL-E has a lot of examples of how that can be executed. The same can be about generating synthetic digital assets. For example, if you want a new style of writing something in front of a store or on a coffee mug, you know what you want to write, you know what object you want that to be written on, and you kind of combine the two and say, can you give me different styles of writing this? And I have an example in the next slide that probably shows about that. Yeah. So a bottle of mouthwash that has the word Skynet written on it, and you would probably never think that this sort of sentence or this sort of a description would exist on the internet, right? Who would search for bottle of mouthwash with the branding of Skynet on it? So this kind of shows how far the model can be pushed. And the images are not that bad. Some of them can be a little crazy because all of these are being generated by a baby model. I'm saying a baby model because it knows all the laws, but it does not know how to jot it all down together. So GPT-3 is still a baby model, and it's capable of putting out all of these images that are just a brain dump from what we've asked it to do. Another really cool example that I have on the next slide is this, an illustration of Pikachu in a suit playing chess. Pikachu in a suit, okay, probably there's a lot of artwork out there, but playing chess in different angles and poses and different art styles, yeah, that's content generation right there. If you probably send this over to an artist, there's going to be a lot of discussion on how this has to be emulated. Is Pikachu going to be in the original style that it was first animated in, or is that going to be in the more recent version that we've seen in films? Is it going to be in that style? Is it going to be in this style? There's going to be a lot of discussion between the person who asked for this illustration and the artist who is making up this illustration. And you probably come up with 4 or 5 different drafts of it, probably after a couple of weeks. But DALL-E comes up with this in a few seconds, and this is just a sample of all of the examples it comes out with. And most of the examples look really, really good, almost at the level of a human artist. And that's pretty cool and scary at the same time. You can kind of go in there and ask for really almost anything, and it munges it up together. It understands what you're asking for, and it puts that out as an image. All right, so that's everything that I've talked about here is what was developed in January. We're in April. So there's probably a lot of progress that's been made over the last few months. And between the time of January and April, there was a model that Google built, and it's a 1.6 trillion parameter model. Like we were talking about 175 billion parameter model, but we're talking about 1.6 trillion now. So you can see, a lot of big companies out there, they're putting all of their computing power at good use and coming up with these incredibly complex models that understand the depth of languages. Our brain works with billions and trillions of neurons, and if you want to emulate the same behavior in a machine learning model, we have to emulate those neurons, right? So you can kind of see these parameters as neurons in our head. So the more complex or the more number of neurons you have in your head, the more smarter you are. So similarly, the more parameters you have, the more smarter the model gets. So the next slide is going to talk about where do we go from here, right? We got this crazy GPT-3, we got DALL-E, we got the 1.6 trillion parameter model, and it just keeps getting better. So something that Andrew Ng, the father of AI, recently had posted about is we need to move our focus onto data-centric approach. So we have the computation to train a model that's, a trillion parameters or, several trillion parameters big. But it's really important to kind of go back to the foundation of where it all started, big data, right? We just have petabytes of data now. And we're training, and we're using that petabytes of big data to power our huge models, huge complex models, hoping that they can make sense out of all of this. They can ignore all of the messy stuff, all of the incorrectly curated stuff, and come out with really good predictions. But we kind of have to go back to the drawing board, go back old school and say that, okay, if a messy data set like the English Wikipedia or, a random scrap of Reddit, if that can produce models like DALL-E, imagine what a properly curated data set is capable of. An example of a really nicely curated dataset is the Iris dataset that's available in scikit-learn. Or you can take the MNIST dataset that's using handwritten digits to recognize different classification examples. So the Iris dataset, which is available on scikit-learn, is a really nice example of a curated dataset. You have data points which are clean and clear. You have different clusters about the different classifications. So imagine if we take the same approach of training this huge model with such a nice, clean, and curated data set. Then I guess that's where we're probably see ourselves in the next couple of years, or probably more, because curating data sets takes a lot of time. You can take it from any number of data scientists coming out there. That data cleaning is probably the biggest job, and that's why we've kind of aligned ourselves towards building these huge models that don't really mind messy data. You can say we're spoiled on computation power. So if you kind of go back and use curated data sets on these super huge models, you get even better results. AI can come up with words that we probably don't even have words of for a lot of actions that we do in our daily life. So that's more or less about GPT-3. And if you've enjoyed this, we have a lot of really cool, interesting stuff coming up at EPRI, a lot of talks like this. So I'll save that. I'll save all of the next upcoming presentations for the end, and I'll hand it over to the next presenter. I think Mukund, you can introduce the next presenter. Thank you.
Okay, there's a question on the chat before we leave, Yashwant, around the power consumption for all these AI compute algorithms. The question is, how are we measuring the energy footprint of these solutions?
Yeah, that's a really good question, right? If you're building models, it shouldn't be in the cost of destroying the atmosphere, or at the cost of not utilizing green energy. So if we kind of go back to Moore's law, it says that the power of transistors kind of peaks at the point it kept doubling over the last 10, 15 years. But now we're kind of at a point where we have to go back to the drawing board and realize that are these computing algorithms, are these computing architectures efficient enough to do processing? So I think Google is doing an extremely good job of building reworking the entire TensorFlow using TPUs. We're using a lot of parallel computation. So I would say 5 years ago, we would probably be using 20 times the power we would be using right now to train the same model. So as time goes on, I guess we're getting more and more efficient of using these algorithms. No matter how big the computation is, we have a way of optimizing learning algorithms and hardware architectures to make sure that the computation happens smoothly and as energy efficiently as possible.
Thank you. Thank you. So on to our next speaker, Ram Rajgopal from Stanford. Ram, over to you.
Hi, Mukund. Hi, everyone. Thanks for having me over. It's been a very interesting group of presentations. Today, I will present some work that we have been doing at Stanford on kind of mapping the existing energy infrastructure. And it was a new type of work for us, but it has yielded some interesting results. So, oops. Sorry, there is some, okay. Yeah, so, we are seeing, the decarbonization of the grid demands due to climate change have established pretty ambitious goals. So, for example, by 2050, we are expecting the deployment of wind energy to go from 2,300 terawatt hours that we have today to 45,000 terawatt hours. In terms of distributed solar and storage, we're expecting deployments of 3,000 terawatt hours by 2050 and 1,290 terawatt hours of energy consumed by EVs. And one of the things that we need to know is where all of this infrastructure actually is, because both it affects how much power they produce, but it also helps us understand what were the drivers of adoption and what is the impact on the system. Right now, we have fairly good, I wouldn't say excellent, but fairly good geospatial databases of conventional energy. They are obtained through various different methods, from kind of authoritative resources, which means, paid surveys and so on, to kind of voluntarily contributed data. So you can find information on the world's coal power plants, the global oil and gas infrastructure, and the large scale electric power plants, thermal power plants. But when you look at renewable energy, that is not the case. So far, we don't have a comprehensive database of renewable energy generation, solar, wind, and the associated infrastructures like the distribution network and transformers for distributed energy, as well as the types of and locations of utility scale plants. So typically, you might have some information, but we don't know their exact locations and capacities. And there are really good projects that have been started that rely on surveys and some crowdsourcing, but typically we find that they lack completeness and the availability of exact GPS locations. And one of the things this has done is really hampered the ability of both, the industry in general, so utilities, as well as researchers and policymakers, to understand the impact and the root causes of adoption of such technologies, particularly, distributed energy resources. So we put the team together slowly around this question to figure out how can we do this mapping. It all started with two students. One of them was Jicheng, after a visit that we had to PG&E, where they said, well, we would love to know where all the rooftop solar in our system is. And they kind of built a method to detect all of that. Our team now has both faculty and students, of course, here from Stanford, as well as other universities like Ben and Lucas are from Oxford. And then we have some partners that we have partnered with, which focus on providing us with the satellite imagery. So what is the idea that we had? Well, if you look at satellite imagery, you can certainly see, these objects, and you can then likely use some machine learning and detect them. That's how we started. And we went on to build, maps of solar installations, wind installations, and I'll show some of them. We are now working on coal mines and hydropower dams. But now when you look at satellite imageries, it's not so easy to detect distribution lines. The resolution is just not there, and you're looking from the top down, so it's hard to actually see these lines. So what we found is then you want to bring in other data sources. So we, like Street View images and OpenStreetMap, and now you can kind of build models for distribution grids. But now there's stuff that is not exactly visible through imagery. So how do you detect those, like EV chargers? So that one, we're just starting to do work on that. And one of the things that we are finding is that you can start using data such as building permits, as well as Twitter information and so on, to start to locate where these chargers are. And as you create all these layers of information, you can combine them with environmental and socioeconomic information to get really unique insights about the system and how it has been built so far and what the challenges will be. So let me just show you some examples. So we started with deep solar. In 2016, the students heard these questions with me and my colleague Arun when we visited PG&E. And we came back. Jicheng asked if he can maybe do some experiments in trying to detect these panels out of some images and so on. And he said, okay, can you approve some budget for that? I said, sure. You think it'll cost you like a few $1,000s to run this stuff. So 4 months later, Jicheng and Jafan came back with a whole map of the United States with all of these panels detected, and they leveraged an existing model from Google that was built on ImageNet and so on, and at the time it was the Google LayNet model, but of course you have to retrain parts of the model to help it segment the panels and measure their areas. Now, the one interesting point about this process is one, a couple of students could do it. They spent a substantial amount of time labeling images, so you have to go and find all the locations and mark what are panels. But they use a semi-supervised approach because you can't generate a massive amount of labels, and so you want to rely on some of the properties of the neural network itself that segments images and so on. But the last piece that I think is important, the previous speaker said, well, computation is not a challenge at all. I not completely agree with that because the costs can be staggering. So to run this neural network, we did 2 training runs, and then we actually ran it over 1 billion images to build a map for the United States. The whole cost was about $70,000 in cloud computing costs alone. And of course, the student costs and all that. If you think about this as something that we want to do worldwide, and typically you're doing out of support from NGOs or public research funds, it's not, we are not yet there in terms of a framework. So I really find that the ability to generate this data, store and share, like Guha was mentioning, will be very important, and it will also create some equity in how we can produce this stuff. So here's just some statistics of what we did then. Processed 2 billion tiles. we located 1.5 million panels. So this was about 15 or 20% more than the best database out there, which is at NREL. And that's understandable. You know, NREL has to process all of these documents and so on and so forth that are contributed by different states and etc. But you can see the performance was pretty good. And one of the things that we had to change in this neural net was to make it faster. So we had to simplify it to be able to run in all of these images. We then partnered with Kevin and another student to kind of do the same for Germany. And the twist that we added there is in certain states in Germany, they have 3D building data. So there's some LiDAR information as well as some 3D building data available for many states in Germany. And you can use that to then extract, you know, azimuth and tilt information for the installed panels as well. So very interesting. And then more recently, we were asked this question is, okay, you know where things are today, but to understand adoption and the economic drivers of it, you kind of need to know when they were installed. And it turns out the big challenge there is like, this is the image today, but as you go back, you know, the satellite imagery is not uniform. So again, you have this heterogeneity of images and you have to align and register them. So there is tools like Google Earth or the Descartes Lab platform that allows you to do this, but again, goes into what Guha was saying about data and having it in a way that it's quick to use makes a big difference. But you have to create methods now that can figure out that a panel is here today. Can I look at lower resolution images and say whether a panel was there or not? We were able to do that, combining ideas from statistics, traditional statistics, and deep learning. And our performance in detecting is that we get about 86% of the dates on a test set that we have exactly on the money on the terms of the year. You can't see the animation here, I think, but basically it shows, in Massachusetts how the adoption happens. And what you would have seen is these dots. It's very heterogeneous. So you would see certain concentrated areas, most likely high income areas, and then some adoption hubs around it. And one of the things that we were able to do is using this information, we can do analysis like the one shown here. For example, we found that, you can ask the question, if I look at all the city blocks in the United States, do we have even distribution? So the number of systems installed per city block is kind of even. And it turns out it is not, because evenly distributed in this plot would mean they follow this line. So 20% of the city blocks would have 20% of the installed systems. But what we can see that's kind of interesting is if you start in 2005 all the way to 2016, it's becoming more even. We also calculated what we call the acceleration of adoption. So that is the rate, the ratio of the adoption rate from 2007 to 2011, and then looking at 2012 onwards to today. And the reason it's kind of interesting is because you could now start to see who started accelerating the adoption rate more. And we plotted that against median household income. And it's kind of very interesting that what you see is initially, panels were only adopted for very high income folks. But now you see an acceleration around this still high, but not the highest income folks. But all of the low income and middle income neighborhoods, their acceleration rates are very, very low. So that's certainly something we're going to have to address if we want to have an equitable system transformation. Our collaborators, Kyle Story and Lucas Krutwagen, sorry, I forgot to put his picture here, actually did a global utility scale solar farm census. So they're using much lower resolution imagery from Landsat, and they were able to detect, 68,600 facilities around the world, 78% of which did not exist on public data sets. With Andrew Ng and his students Jeremy and Sharon, we have been working on applying these same techniques to locate wind turbines and wind farms in the United States. And one of the challenges here is, wind turbines are a little bit, wind farm is a little bit more spread out than a solar panel. Also the shape of the object and the locations which are not urban, so the contrast in the image is lower. So you need a few different techniques. But again, with a group of students, a couple of students, maybe a quarter, we were able to get fairly good performance. And now I think the accuracy of this model is about, accuracy and recall are about 88% and 90% or something like that. We are actually building a database for the United States and for Brazil and India to showcase this method. And one statistic that's published by the EIA is that, in our existing databases, we have about 50% of the installations missing. So that's kind of an important thing. So now we had all of this supply side stuff. We started looking into, can we actually map transmission and distribution? So transmission maps are available to an extent. You can find them, in open data sets. But we found distribution maps are available in a very limited way. And particularly if you go outside of the United States, you have a difficulty for both transmission and distribution. So we were looking at Africa and Brazil and India as examples of places where you don't have this data readily available. And we struggled with this. We spent a lot of time thinking of how to do it with satellite imagery, but we had an intern in the summer and he observed that, look, if you look up on Google Street View, that's something that I didn't know you could do, you can actually see all of these lines. And so again, you can now combine some deep learning to detect all the lines on that are, that you detect, and then use some interesting methods to kind of combine them and interconnect them to form the network. And we have some initial published results on this. We're still writing a more definitive paper. We get a pretty good performance. We are testing it on, publicly available data here, published by PG&E for the Bay Area. But we are also planning to apply this in Uganda, I think, and Kenya. So it's a pretty interesting model. You can detect all the poles, you can find transformers, and you kind of build this map. So, but one thing that we were able to do right away is to say, which are the lines that are overhead? Because you may ask, how do you do underground lines? So for underground lines, what you use is some existing data sets that allow you to predict the whole network without even having an image. So it's the most likely network. You don't really know if that's completely correct. But just using this detection of whether the line is underground or overground, we were able to look at fire risks in the Bay Area. So we are just submitting a paper on that. We wanted to know, we have the percentage of lines that are underground, that's we call undergrounding rate of a county or of a zip code. How does it correlate with wildfire probability risk that is calculated by the state of California, but by CAL FIRE? And what we found out was that the undergrounding rate, it's actually does not correlate very well, in the sense that you have higher undergrounding rate of these lines where you have lower wildfire probability risks. And we have ways of assigning these risks into the locations of the lines and so on, which we explain in the paper that we're submitting. But moreover, if you actually look at, household incomes of all these different zip codes or census tracts, and you look at the undergrounding rates, again, wealthier folks enjoy more of a higher undergrounding rate. And the reason why this happens is not just, some kind of prejudice or something like that necessarily. What we found out is undergrounding focused on high housing unit density areas, and they turned out to be inversely correlated with fire risk and population income. Okay, so that's another kind of issue that we found. As a last project I wanted to share to end the presentation here, we are actually using our deep solar detections. We are using our distribution information and trying to generate EV profiles to look into like a planning. So in this picture here, you have location of chargers, solar, wind, etc., and giving a tool for planning. All of this is kind of done in open source. So we publish all the code. We are figuring out how to publish the data. So that's a conversation that's been ongoing for a little while. And this year we're starting a DOE project on this as well. Okay. So
thank you, Ram. Thanks a lot. The great presentation. In fact, I have a couple of follow-up action items that I think maybe SCE and Stanford could also work on some of these topics. So thank you so much. So now we come to the panel discussion. So I want to invite all of our presenters back online on video so that we can get the panel started. And while we've been asking questions that have been asked by the audience along the way, I'm going to start with the very first question that has been brewing in my mind, which is we've heard about the importance of data for AI. And so the question really is around how do we foster more effective data sharing between utilities and AI vendors? So maybe Ram, I'll start with you from an academia standpoint, and then maybe Dave, turn it over to you from a research standpoint.
Yeah, this access to data is a huge issue. Just in the project we presented as an example, initially we used and mined the data from Google Maps, but Google changed their access policy, so you can't download and use those images anymore. So we had to partner with Maxar and basically negotiated some academic rates for access to the information. With utilities, what we found is that once you have a reasonable way to deal with your data security, they start to have more openness if they find a use case interesting, but it's still, the whole process takes 1.5 years. And as you can see in some of these examples, we are able to produce results in 4 or 5 months. So it takes longer time to access the data. And the last piece that I wanted to say about access to data, so there's a challenge to accessing data itself, either because it's commercial or it's locked in a utility, and information that could benefit utilities. But there's also a challenge of like maintaining this information. So for example, for deep solar, we need to regenerate these maps every year if we wanted to have it all up to date. And that's really, universities are not a great place to do that. So that's kind of a big challenge that we see.
Dave, any comments from you on this topic?
And REL that are research in this area are we work with a power system engineer that typically will use some kind of IEEE test system when they're building out algorithms. And of course, those may have no bearing on reality for what a real power system or real utility company is looking at. I think the creating models and simulation where you're missing significant portions of the data set, like what certain parts of the system look like, is a really big challenge for us. I think one of the promises of using these model-free approaches is that there's the hope that given only partial information or partial observability of the system, which might be provided by a utility company and might be provided by sensors, is model-free methods kind of show some promise in dealing with that because they can kind of fill in the gaps. The last thing I'll say is that we think a lot about privacy considerations as well, and it's even in the algorithm one of the algorithms I talked about earlier, that we chose an algorithm where communication between agents or partitions on the system, that communication is minimal and internal decisions to that partition are never shared. So I think even because I'm more coming from the algorithm side, I think it's really important to think about that data privacy component when we're building algorithms. But as far as, I would love to know more about how, what the future looks like for these utility companies and other stakeholders sharing data and what a mechanism like that would look like. As somebody who's more, on the computational algorithm side, I don't know the answers there, but I'm very interested in that topic because I think it's something we see a clear need for.
Yeah, so I think as a utility itself, I think we are trying to work with both vendors as well as other industry folks to share information, because one of the big thing is to share information. And while we may not have all the AI engineers within the utility, we want to figure out a way to enable sharing, but keeping privacy also important.
And it's
The
not,
second
if
question
I could
is,
just say one more, oh, sorry.
go ahead.
One more thought there is that, I'm on a project now, which is a transformational R&D project. And there's the notion that there's a community called Pena Station being built in Denver. The community of like 100 smart buildings, and they're kind of building it from the ground up to be almost an experiment where we can basically things can be tried. You can kind of from the ground up design, to make sure that you have the data, you have the control infrastructure and all that to see how these algorithms might work in a distributed system in real time. And that's great. But of course, you can't really expect to be able to build power systems from the ground up more generally. So I think that's where there's an interesting and challenging direction is how to kind of take what already exists and figure out how to get the data you need from the existing system.
Okay, thank you. I think the next question I want to go about is, we heard a lot of great things about AI and what AI can do, but what are some of the key enablers to help utilities adopt and utilize AI? Maybe start with you, Yashwant, first, then maybe go to Ramanathan with you from a Google standpoint, and then maybe end it up with you, David. So Yashwant, do you want to take this in terms of what can utilities do? What are some of the key enablers that utilities need to do to adopt AI?
Absolutely. So this is a area of interest. AI, ML. I know it's been getting more and more popular over the years. One of the key challenges of utilities adopting AI is the lack of modern data collecting procedures. So there's a lot of data stored in hard copies, like a lot of reports that have not been digitized yet, or a nuclear power plant that's not modern enough to have the recordings of meter readings over the last 1 month or last 1 year. So this is an extremely big challenge, and there's an AI approach of solving that as well, where we have a bunch of projects at EPRI where we're building models capable of reading the readings on gauges, on different gauges, to tell what sort of reading is on the gauge, and trying to predict what a more analog system, converting an analog system to a digital system. So there are approaches that we're taking in the data-driven decision-making sector of EPRI, where we're trying to modernize a lot of nuclear power plants and utilities to make sure that they're using all of this data that they have into a more digitized format, and then pushing it over to AI ML models. And I think I'll hand it over to Ramanathan to talk more about this. But yeah, we're getting there.
Thank you.
Hi. I don't think I'm qualified to talk about what utilities should do. I just get power from them and send them money. So
Okay.
I'm going to draw an analogy to something in the many years ago in the development of the internet, in the context of the role of the private sector and the role of academia. So we've all heard about how the internet was developed in academia, in Stanford, in UCLA, and MIT, and so on. But the interesting thing is that though many of the core technologies were developed there, you had to distinguish between the technology development and creating an infrastructure which everybody can use. For that, they used DARPA gave contracts to BBN and it out. And the point is that you need an infrastructure layer that people can actually rely on and build on top of. And I mean really rely on in a reliable fashion. None of the stuff about, oh, it's so sophisticated we can't actually tell you what it is and all that stuff. But it needs to be workhorse. You shouldn't have to think about it. Unfortunately, now we're in a situation where there's things, thanks to the different clouds that are there and stuff like that, we should be able to do. And the teams like Ram's team, Arun's team, and so many other teams shouldn't have to go about scrounging for $60,000 a year of cloud credits and $70,000 there. There needs to be a national infrastructure generated their data. It shouldn't be the case that their group has to keep the data updated. Otherwise, the data sets do we have across the web which are just dead, right? I mean, this is like they were updated last in 2015. Yeah, I'm okay. This thing is missing. Student has graduated. You can't find it. So we need to think about what is the structure of that sort in order to support this kind of work.
Thank you. David, do you want to run out the first question in terms of the key enablers for utilities to adopt AI?
Mukund, is that for me?
That's for me.
Oh, sorry.
Yeah, so if you want to comment on that, like what are some of the key enablers that utilities need to have to adopt AI?
Mukund, on my experience on having worked with utilities in some projects that are now actually used by utilities, we created this open source tool called Wisdom. I think there needs to be someone knowledgeable about data science on the other side, but also some type of strategy where utilities determine what are some problems they have where they are open to actually using AI and changing their processes. A lot of the times what we found is not really about the methods or the accuracy, it's about the decision process and how you should go about doing it. Because with this type of information, you would do it differently. So Wisdom, we created it around 2013. Now PG&E writes regularly reports using it, but it took about 8 years. And a postdoc who decided to be kind of permanently engaged on that. So I think that is a change on how do you go about making decisions now that you have data. I think that's another conversation we need to have at some point.
Okay, I'm going to take a question from the chat. There are two questions that are sort of connected. One is around public data sets of grid or distribution side of power. So are there public data sets of grid or distribution side of power quality, example, grid frequency, phasor, THDI, etc.? And then associated with the same question is around the privacy. What are some of the privacy elements around sharing of some of these data sets? So maybe Ram, because you've worked with public data sets, and so maybe why don't you start there, and then maybe we'll go to you, Ramanathan, and then to David, and then Yashwant.
Yeah, I can share on the Deep Solar project. So once we had the project, we wanted to publish both the data set and the code that allows us to do that. And the code was a no-brainer. The university immediately approved it. The data set, because it contains individual detections of solar panels, there is this issue of privacy, and there's a lot of worry that publishing that, could be sensitive and so on. So what we were able to publish was, block level, city block level aggregates. And right now, there's kind of an ongoing conversation inside of Stanford that goes beyond this project and encompasses many other projects, which is there is a way to share data when the data is medical data, so that the university is able to do that, and they screen and vet people, and you submit a small proposal and so on. How do we do that for the energy data when we are talking about distributed information? I think that's kind of a big piece. The other piece I've been told was security is a big issue. We cannot share our network information. I just wanted to counteract that with, we have demonstrated now, you can actually map all of this information using satellite imagery. So, maybe we need to have a little bit of a different attitude and understand the purpose and the groups that are accessing the information and whether it's good for the energy system, and go from there.
Cool. Ramanathan, do you want to take a crack at it? We can hear you.
So as you might have possibly seen, Google and privacy and all these things have had in the public media in the last decade or so. My advice is, I don't think it would be a good idea for universities to each individually go and develop policies. You're going to get a patchwork of probably most likely inconsistent policies, which are going to be that you're going to find some people in some universities who are incredibly cautious, others who are less cautious. I would actually look to someone like the Census Bureau to set up policies. And in fact, that's what we've decided in Data Commons, which is that if the census says it's okay, we are okay. And if the census says it's not okay, well, government go talk to census first. And the census actually turns out, the US Census Bureau actually turns out to be quite reasonable because there's so much, on the one hand, in the world of privacy, you have people who believe that you need to take a fairly extreme position and have everything be differentially private. There's others who believe that the utility, so much of public policy and so on rides on the availability of this data that the whole issue is more nuanced. And in our discussions with people at the Census Bureau and BLS and a few other of these organizations, they're actually incredibly sophisticated and they're thinking about this, and we are looking to them. And it would be great if the academic community could push on them to establish sort of guidelines for what kind of a data should be released and should not be released and so on. And now I'm of course talking purely about privacy. I'm not talking about national security. There's a point has been made that just having the network of all the power generators and so on and so forth may possibly lead to some security issues. That's a different issue altogether. But just in terms of the privacy, my personal or my suggestion, the approach that Data Commons is taking is to look to these government organizations for leadership.
Thank you. Thank you. David or Yashwant?
Well, I am not a good person to ask about open source data sets. I will say that we're very interested in NREL anyway in open source algorithms, and so I see a great, kind of union there of needs. These open source algorithms need good data sets, and so we're, I'm interested to learn more, but I'm not a great person to ask about that. But we're all about the open source release of software as as needed to kind of help vet these data sets and use with the data sets for sure.
Thanks. Yashwant, I know at EPRI you guys are working with a lot of data sets. So have you guys come across any openly available data sets that utilities are contributing to?
Yeah, the availability of data sets is quite a challenge, and we at EPRI have tried to take that challenge head on. So I believe we're building a data set source called EPRI 10, which you can actually check out right now at ai.epri.com. So the initiative is to collect all of these data sets from different energy utilities, make sure that there's no personally identifiable information on it, try to make it as anonymized as possible. So that solves the data governance issue, solves a part of the data privacy issue. But we're still in the mode of collecting data sets and curating them so that these data sets from energy utilities are being optimized for ML algorithms. So if you want to take a crack at it, you can just go to ai.epri.com and sign up for the newsletter. Apart from EPRI's initiative for collecting data from utilities, there has been an explosion of open source data sets out there. I'm pretty sure data science enthusiasts would all know about kaggle.com, but another great resource is datasets.google.com. And I think this was released a couple of years ago. And it's an amazing source of open source data sets. Like it gets kind of exhaustive to make a huge list of all the links of open source data sets for, like, example, data.gov. But if you go to datasets.epri.com, it's like an advanced search engine for all the different datasets available. And these datasets include websites where it's legally absolutely all right to just web scrape all of the data available on those websites. So those are a couple of really great resources to get started on.
Okay. Now talking about large-scale data sets, one of the questions that has come up in the audience is around utilities have a lot of good quality data, but all the data is not sufficient, or the quality is always is not there. I've seen that firsthand, even at a CE, and also the consistency of the data between systems. So whilst we have a lot of data sets that are needed to run all these AI algorithms, there's a lot of inconsistencies and bad quality. So what are some of the techniques, or have you seen any advances in terms of improving the ingestion process and the lack of data and the gaps? Is there any? What are some of the techniques that you and your teams are taking to overcome this particular gap? And maybe again start with maybe you, Ram, and then others can chime in.
I would say there are, data quality and cleaning data can be a whole black hole that can consume all of your time trying to achieve perfection. So one of the things that we started doing is, trying to see what can you do with minimalistic amount of data cleaning. What we found it's a much bigger issue is really the formatting of the data and kind of correlating them across different data sets. That takes its own time, and you're uploading data from multiple sources in some of these projects that I shared. And I think Guha just did on his presentation really kind of nail it. If all of these data sets were already with the right format for access, and we had the template or whatever the information structure in there, I think it would have shaved maybe another 20% of the time, 30% of the time of the projects. But yeah, so my take on data quality is very simple algorithms for bad data, and then try to work with it. But we end up spending a lot of time on kind of data organization and correlations and things like that.
If I may add, Data Commons is looking for collaborators, especially in this space. If you have data sets that you want to make available, and the real value of having, I helped build data sets, the schema.org underlying thing, but data set search is, at the point you're at a data set and then you go have fun. The whole point is to do something like what the Sloan Sky survey did, to create all of this thing in an aggregated fashion, clean fashion, once and for all. And the nice thing about doing that is that the value of data increases combinatorially. If you would like to figure out exactly what is the correlation between, say, the conditions, health conditions indicated in CDC 500 with the various energy things that Ram and team are doing, that would be great. And if you could do that additional correlation without any extra work, wouldn't that be fantastic? And so I really strongly feel that is the future of how data organizations are going to be the platform upon which real AI, not fake stories, is built.
Yashwant, you deal with a lot of data sets that are coming into EPRI, and they may not be completely clean. How is you and your teams dealing with the gaps?
Yeah, as I've mentioned in the presentation, big data we're here, we're in the era of big data. There's no shortage of data, but here we kind of have to go back and make sure that these data sets are properly vetted for machine learning. There's a lot of problems with the data sets that we've spoke about on day one, biases, a lot of anomalies that shouldn't be appearing in the data sets at all. So there's a couple of approaches that I personally take at EPRI in order to manage these messy data sets. Is one, I just go to my subject matter expert and say that, hey, this does not make any sense. Does this make sense to you? Because that's the most direct feedback I can get regarding a data set that I'm not that I don't have any sort of a specialty in, right? I'm just the guy who builds the pipeline and makes sure that the predictions are intact, but I have no subject matter expert. So I just go to the expert and say that, hey, does this make sense? Because this is not looking right to me. So based on the feedback, I make changes to it, or I try to build a model which is capable of correcting all the misinformation. One of the examples I can talk about is anonymizing PIIs, personally identifiable information, like phone numbers, names. That's pretty much easy to do, and there's an open source software out there that does that for you. But if you're talking about nuclear power plants, there's a lot of sensitive information in it, including component names, system names, different types of maintenance procedures, and the costs associated with it. So all of these need to be anonymized, and there's a machine learning approach. I curate a new data set that shows that, hey, you need to anonymize this part of it because this relates to a plant component name, and the model starts doing that. So tackle machine learning data cleaning problems with machine learning. I think that's probably the most efficient way to deal with these big data sets with a lot of messy information in them.
Okay. Thank you. I'll take another question that I wanted to answer, which is maybe to your comment, Yashwant. I use a similar comment where you don't turn the technology gun against yourself. So talking about AI, what are the things that AI can do or shouldn't do? Like, what are some of the use cases that you think of in the utility sector, or maybe more generally, that we should not be tackling with AI? Maybe start with you, Yashwant, and then maybe I'll come to you, David, for the same question.
One of the trends with AI is all about caring the quality of the predictions, right? We see the end result and we're like, hey, that's a pretty good result. And we go back and show these results without really caring about how the model actually got that result in the first place. And that's a huge red flag for me, at least in the utility industry, because explainability in AI plays a really important role. Understanding how that prediction was made, what sort of biases did it encounter in that particular data set. So I think bias is a big problem that we personally face with a lot of different utilities. Few utilities use a particular type of jargon, other utilities don't. And if I'm building a natural language processing model that's trained on a different utility data set, and it's predicting on a different completely new utility data set, then the predictions are just going to be all over the place. And if I have an AI black box in place, it's not going to tell me why the predictions are coming incorrectly. So first approach is have a model that is really bad at predicting, but is really good at explaining why it's making this prediction. So not a black box model, but a model that can be open, explained, that can be shown to this best statistician in the company and say that, does this make sense? Is this function? Is this algorithm doing the way it's supposed to do? After that, once we have the ground rules set up, we're gonna move towards more of a black box solution because they're using a CNN for image classification is a semi-black box approach because you kind of have an idea what's going down, but if you start making that model more and more complex, it's going to start making a bigger black box, a darker black box, which just makes it impossible to interpret. So I think interpretability is step one, explainability is step two, and then we move on to the quality of predictions. Because I don't really care if my predictions are all accurate as long as I don't know what I'm looking at, right? So that's a really important approach.
Thank you. David?
Yeah, I think I have a similar point of view on that. Maybe very pertinent to our times. The current time is not just for AI models and statistical models in general, but also even for optimization type models. Are we really taking into account, the well-being of the entire system, which includes the people that live in that system? So we can write down a nice, power flow equation that says, hey, in the event that there's a disruption of some kind, my model, whether it's AI or otherwise, says to cut off, this partition of the system and leave it hanging while we restore the rest of the grid. And there may be no notion of whether, the reason why that's an easy partition of the grid to cut off is because it's a relatively poor part of the city or the community, and it's so minimally connected to the rest of the system
Thank you. Actually, there's a question directly for you, Ram, here on the chat, which is around DeepMind is a weakly supervised CNN. Why do you use the term weakly?
Because we don't really give it a lot of images with labels. So part of what is done is, instead of pointing, you find an image, and instead of pointing exactly in that image where a wind turbine is, you might just say, there is a wind turbine on this image. And there might be multiple turbines, there might be a piece of a turbine. So it is a way of very quickly generating labels in data sets. In my opinion, I think this issue of labeling data sets, it is very critical, and it's going to be a whole industry on itself to have really high quality labeled data sets, because that's what allows these pattern matching based methods, like deep learning and so on. In my understanding, they are like that, to work. But in this case, we were able to get away with not having to outline exactly where the object is. That's what we need.
So speaking about labeling, Yashwant, I know that EPRI is doing some work with images in this space. Can you maybe comment a little bit about that?
Absolutely. So I work more in the natural language processing domain, but I have a couple of colleagues who are very deep into vision. And one of the bigger challenges with images, as Ram mentioned, is labeling, right? We need an annotator to kind of come in and say that this is where the part of the component that you're looking for is. For example, for insulator caps. But we have a lot of data annotation going on because the cap of the insulator is really long. It's taken at a really weird angle, and the annotator must make sure that the box encapsulates the entire entity all by itself. So there could be a lot of different anomalies turning up. It could be an image with no focus. As cameras start getting more and more complex, their focal point changes a lot. And, if you're using a drone to take images, you might be unfocused on the component that you actually want to capture. So all of those anomalies can be handled only by data labeling, data annotation, and that takes a lot of time. So if I just wanted to get started on a vision project today itself, and let's say I have 100 pictures of the components I want to classify, it's going to take me weeks to get through the annotation process. And through the annotation process, I'm going to get to know, all of the different anomalies, all of the different ways my model can misclassify something. Because if I want to detect weighing scales in images, and I have 28 pictures of weighing scales in the shape of a square, if I put in a weighing scale in the shape of a circle, it's not going to detect it because that's a bias, right? So then it all starts coming out saying that here is a really big drawback for a data set. You just don't have really wide variety of examples for a particular class. So I think Ram's approach is much more robust in taking care of the situations. It just says, hey, there's a wind turbine in this picture, go find it. That's a really smart approach of handling this issue. But again, it comes down to data quality. If you want a really smart, robust way of doing it, you just say there's something in this image, go figure it out. Or if you want a model to kind of tag and say this is exactly where the wind turbine is at this particular location, then I think data curation is a really, really important step. And it takes a lot of time. It's okay if it takes a lot of time, but it's going to be worth it in the end.
Cool, thanks. I know we are running out of time, so maybe in the last 8 minutes that we have left, I want to talk a little bit about the future of AI and what excites our panelists the most. So maybe let's start with you, Ramanathan, on this question on what is the what is the future of AI that excites you the most, and maybe limit your response to maybe about a minute, maybe 2 minutes.
Oh, wow. I'm sorry, I have been in this field of AI since 1987. My advisor was John McCarthy, who coined the term AI, who's often been called the father of AI. The thing that excites me, AI is a thing where every decade or so, it's a new thing that happens. It's almost like a religion. We kind of forget what happened before and then go on to the next thing. I've never seen any other engineering field quite like this. It's fascinating. That said, the current wave is around enormous amounts of data, and enormous giant models are built on top of this enormous amounts of data. There's lots and lots of topics where you cannot get enormous amounts of data. If I'm trying to build something that is going to make some predictions about counties or about states or about countries, it kind of gets difficult to go create 1 billion new counties or create 10,000 new states. I just have to work with the amount of data that is there. The second point is that, we as species no one of us would be able to get to the level of sophistication that we are if we were just sort of brought up by ourselves as feral kids, which means that we learn something from others. We're a combination of what is taught to us and what we learn from data. And the ability to be able to combine the two is essential to us. And this is what is going to be required if we're going to be able to create models that work in cases where we don't have billions or even millions or even tens of thousands of examples. There's some work that is, looping back to what it means to have sort of more classical representations in addition to just vectors. And how do you combine sort of teachable systems with learning systems? That I think is going to be very exciting.
Okay, David?
Sure, yeah, I'll give, I guess, maybe two parts of an answer. When it comes to power systems, I think that the future of AI, the question of what that looks like, is very much tied to how to make AI work in a real system. Not a system you design from the ground up, but a system that's in place where you have all this messy issues of data quality, data completeness, maybe imperfect communication across your system, and all these real challenges. I think the success of AI, going towards a truly autonomous system, there is a huge gap right now between where we are and where we'd like to be. So I think as far as power systems go, that's kind of the future. I think a lot of work needs to be put in the next few decades. When it comes to AI more generally, I think there are a lot of interesting things happening right now with methods that are not so much gradient-based, kind of challenging some of the basic assumptions about how to train these big networks that can also help with issues of sample complexity. Finding simpler models that perform more complex tasks, stopping the need for backpropagation, these kinds of technical challenges. A lot of interesting work happening there that I think I'm interested to see how it develops in the next few years.
Cool. Yashwant, you have maybe in a minute or so.
Sure, yeah. The only closing thought on the future of AI is we will eventually get to a point where AI models start making more smarter predictions than us, and that's completely normal. We're biologically, as a species, as Ramanathan mentioned, we have our upper limits, and it's all right for a completely artificial machine to kind of supersede those upper limits in its own way. One of the examples is a reinforcement learning algorithm figures out a new strategy in a game that humans probably never ever thought about. Sorry about that. So why is this cracking up? Just talking about the future of AI. So there's a lot of potential in that space. So closing thoughts. Keep an eye on the reinforcement learning space, because that's something we humans can kind of relate to. Playing games in ways that we never thought of. For example, watch an AI play Mario. It's going to play in a way that you've probably never ever seen it before do that, because it cares about its reward, and it's getting it through a strategy that we couldn't probably even come up with during our lifetimes. So really exciting for the future of AI.
Cool. And Ram, as a faculty member at Stanford, maybe what is the academia working on, which is exciting for the future of AI?
I think there's a lot going on in Stanford, but I can say maybe some of the things that I find challenges with which we want to use AI to address. I think one is the intersection of climate and power systems and grid. I think it's a very difficult problem, partly because you don't have as much data as you would like, and you need to incorporate some of the domain knowledge. The other area that I find will become very important, and we're starting to see this in some of the projects we do, is there is this kind of older concepts around knowledge bases and so on. And if you want to do inferences that are not just a pattern matching with the past, you need to start incorporating that into the more modern systems. And I think in energy this is very important. Again, it's the scale of data you might have is not the same as like all images in Google Images. That's like a different scale. And the last piece is, I think, is students. So we are producing a lot of amazing students. So I think that will continue. And I was hoping at some point they could go into the power industry more regularly.
Absolutely. So on that note, we'll call it time. Thank you everybody for attending the last 2 days. It was great to see the participation, and I really thoroughly enjoyed both the day's session. Again, there's a lot of information on the EPRI website. There's an upcoming reverse pitch that is being scheduled for the month of in the next couple of months. So please stay tuned for that. And again, thank you to all the panelists. Thank you to EPRI for organizing this event. And everybody have a great day. Be safe.